Alright, 12.4 is the probability of compound events. Remember, our probability could be expressed in three ways, right? As a fraction, with the word to, or with a colon. Okay, so we're kind of back to that. I think that was 12.1, is that right? Maybe? That we did that? Alright. I'm just going to kind of read through this first paragraph here. Okay, it's pretty important for us. It says, when you consider all the outcomes of either of two events, A and B, you form the union of A and B. Okay, so we're talking, we have two different things, and we want both of them. Okay, that's called the union. That's going to be specified with just the, like, it would look something like this. Okay, A union B. That means A and B. Okay. When you consider only the outcomes shared by both A and B, you form the intersection of A and B. Okay, so that means that's basically OR. Okay, so the union or intersection of two events is called your compound event. So we're going to be talking mostly like this. Okay, so this reads A and B. This reads A or B. Okay, this is the one we're mostly going to be working with today. Okay, that's going to be our compound event that we're talking about here. Okay, the next thing we need to talk about, and I'm not going to draw these diagrams, but let's take a look at those three diagrams we have on page 724 at the top. Did everybody see those? Okay. The first one, okay, it shows the union of A and B. Okay, that would be them combined together. Now, obviously, some of those are counted twice, aren't they? Okay, so if I was looking at A on the first diagram, there's 2, 4, 6, 8, there's 9 things in A. And if I was looking at just B, 2, 4, 6, there's 8. But how many of those are in both of those? There's 4. Okay, so just keep that in mind as we're going on here. Okay, the second one, or the one in the middle, has the same thing, but it's wanting the intersection of A and B. Okay, so right there, the paragraph there tells us to find probability of A or B, you must consider what outcomes, if any, are in the intersection of A and B. Okay, so we got to think about which ones are in the middle. Okay, how many of them are being repeated? Okay, if there are none, for example, the far right diagram, okay, that's what we call mutually exclusive. Okay, that's a good definition for us. Mutually exclusive. Basically, what that means is that the two things you're looking at have nothing in common. Okay, they're completely separate. Okay, so your two events, I'm not even going to say two, let's say events have nothing in common. Does everybody see how that last square there would be mutually exclusive? They're not overlapping. They have absolutely nothing in common with each other. They're just two separate events. Okay, in that case, if I want the probability of A or B, okay, I would find the probability of having A, and then I'd find the probability of having B, and I'd just add them together. Okay, and we'll get into more of that here in a second. Okay, if A and B are not mutually exclusive, then the outcomes in the intersection of A and B are counted twice. Okay, that would be like the first diagram. Okay, we're counting 4 of those twice, right? Okay, if that's the case, okay, we need to subtract what we're counting twice one time. You guys get what I'm saying there? Give me head nods. No? Okay. So we have, in this diagram, I'll go ahead and draw it. Okay, so they give us this Venn diagram. Like this. Okay. I want to find the probability of A or B. Okay. Not both of them together. I want A or B. So we have 1, 2, 3, 4, 5, 6. Okay, maybe there's 7 in A. Okay. 1, 2, 3, 4, 5, 6 in B. Okay. How many of those are in both of them? 3, right? These 3 middle ones. Okay, so I'll put those into green. Okay. Now when I do that, here I have 1, 2, 3, 4, 5, 6, 7 reds, right? Okay. So I have 7 out of what's the total? Well, 7, 8, 9, 10, right? Okay, so I have 7 out of 10 probability there. Plus, how many blues do I have? 1, 2, 3, 4, 5, 6, right? Now, if I had just those 2, just like that, that's over 100%, right? Probability cannot be expressed over 100%. You guys agree with that? It has to be between what 2 numbers? 0 and 1. Well, the reason this is over 100% is because how many times did we count the green ones? Twice. Okay, do they exist twice? No, they just happen to be in both A and B. So we have to get rid of one group of that. Okay, so instead we counted 6 here. We need to get rid of how many? 3. Okay, so we got to subtract that out. Does that make a little bit more sense? So now 7 plus 6 is 13 minus 3 is over, which it should be because that was all we had, right? Okay, so we should have got 100% or 1 to 1 or 1 or 100%. This one would have reduced. Okay, so there would be your 3 possibilities for answers. Does that help, Lorelai? Say you were one of the shaking your head no. Okay, so we're getting rid of one group of this because when we counted this, we counted it twice. Okay, is all that's happening. Okay, so let's take a real quick look there in the green box. Okay, it's exactly what we just talked about, but let's go ahead and put it into words. Okay, if A and B are 2 events, then the probability of A or B is blank. Okay, now that would be if they are not mutually exclusive. So let's do that. Not mutually exclusive. What did mutually exclusive mean again? They had nothing in common, right? So if they're not mutually exclusive, they have something in common. Okay, be careful with that because that seems a little bit backwards at times. Okay, but if that means there's something in common. So for the probability of A or B, if they're not mutually exclusive, is going to be what we just did because these had something in common, right? Okay, so I need the probability of A plus the probability of B minus both of them, right? The ones that where I had both, right? Didn't I subtract both? Okay, so then I would subtract the probability of A and B. Okay, that would be if they are not mutually exclusive, meaning they do have something in common. Okay, if they don't have anything in common, that would make them what? Mutually exclusive. if they are mutually exclusive and have nothing in common, then my probability is actually a little bit easier. It's the probability of A or B equals the probability, one second, my board's messed up, the probability of A plus the probability of B. Which we already learned that, right? We already knew that if it said or, we were going to add, right? Because and means multiply. Okay? The only catch is if they actually have something in common, you're going to have to subtract that one, or that portion of it. We'll do some examples here in a second. Just make sure we have that down. Okay, so example 1 is actually mutually exclusive, which I think the mutually exclusive ones are going to be pretty easy for you. Okay, they tell us that a card is randomly selected from a standard deck of 52 cards. What's the probability that it is an ace or a face card? So what two probabilities do we have to think about, Brody? Right, so Devin, what is the probability of getting an ace? Which is 4 out of 52, which he just reduced to 1/13. Okay, because I guess you could think of it as in a suit, right? Okay, so the probability of an ace is 1/13. Okay, and I have to add to that because that's or, right? And they're mutually exclusive, so they have nothing in common. Or a face card. How many face cards are there? There's 12, because there's 3 in each suit, right? So there's 12. Well, if there's 3 in each suit, then my ratio is what? 3 out of 13. Can I combine my like terms and solve here? Yeah, what do I get? 4/13. What's another way to express that? You're going to have to use the calculator today. .308 or 30.8%, right? Most of your answers today, it looks like they're looking for decimal answers. Okay, so just be aware of that. Okay, now the next part, example 2. I didn't know that was still following me. Okay. Example 2 says a card is randomly selected from a standard deck of 52 cards. What is the probability that the card is a heart or a face card? Okay, do you guys see the difference? Ace and face card were completely separate, right? Because there's no way to have both of those. Could you have a heart that was also a face card? Yes. Okay, so is this mutually exclusive or not mutually exclusive? Not, because there's something in common. Okay, so the probability of a heart or a face card. Okay, well, what's the probability to get a heart? 13 out of 52, which is 1/4. Okay, what's the probability to get a face card? 3/13, right? Now you can already see we probably should have left it as 52 because you're going to have to change them anyways. But then, how many of them are face cards and hearts? 3 out of 52. Okay, so we should have just left these as 52. Well, that's okay. This would be 13 out of 52. This one would be 12 out of 52. 13 plus 12 is -3. So it's 11/26. As a decimal, 0.423, which is 42.3%. Okay, the hard part's going to be deciding Is it mutually exclusive with nothing in common? Or is it not mutually exclusive where I could have both of them at the same time? They did give you a Venn diagram there of that scenario also. Okay. Let's skip down to example 3. Okay, we'll just keep moving here. It says, last year a company paid overtime wages or hired temporary help during 9 months. Overtime wages were paid during 7 months and temporary help was hired during 4 months. At the end of the year, an auditor examines the accounting records and randomly selects 1 month to check the company's payroll. Okay, we want to know what is the probability that the auditor will select a month in which the company paid overtime wages and hired temporary help. Okay, so they give us our diagram there. Okay, and we have the probability of A or B. Okay, so let's just take a look at this. You are going to have some problems like this right off the bat in your homework. Okay, now I know with A or B, are they mutually exclusive or not mutually exclusive? They're not, because they have something in common, right? Okay, so I know from up here, okay, so not mutually exclusive, I know that I need to do the probability of A or B equals the probability of A plus the probability of B minus the probability of both of them, right? Okay, I know that. Okay, they want to know, again, what is the probability that the auditor will select a month in which they paid overtime wages and hired temporary help. So basically, we're looking for the and portion, aren't we? Because we want to know, what is this? Okay, because I don't know. So when you get something like that, just take your probabilities that you know. What is the probability of A? Well, how many are in A? There's 7 out of a total of how many months? 12. There's 12 total months, right?
During the 9-month period.
But it's out of the whole, like, that 9 months was when we did that, when we hired workers or paid overtime, but there's still 12 months that could be checked. Okay? You guys follow? Because, well, and then you count all your dots. There's 7, right? Actually, that's not going to be right. That's only going to be 11. 2, 4, 6, 7, 8, 9, 10, 11. So 12 is your total months. Yeah. Because they can still choose. Just because they're coming in to audit you doesn't mean they have to choose from those 9 months. Right? They could choose any month. Okay? So you have 12. What's the probability they choose? B. 4 out of 12. Okay. So together, this is a bad example because you could do this just like our first one we did. Okay, but what they're doing is they're telling me that the probability of A or B happening is, they're telling me it's 9 out of 12, which is correct because how many total months did we have to do this for? 9. Now, to get to 9, using our diagram, we could have just done 7 plus 4 minus 2, right? Okay. What they're trying to show you is that you can set up an equation depending on the information given for you. And solve for this, is what they're trying to show you. They just didn't use a very good example. Okay, so here, well, what would I do first? Think of this as just a variable. Okay, add them together, so you get 11 twelfths, and here you get 9 twelfths, minus probability of A and B. Subtract, and you get, what's 9 twelfths minus 11 twelfths? Negative 2. 9 minus 11? Right? 9 minus 11? Negative 2 twelfths equals negative probability of A and B. Divide by your negative and you get 2 twelfths is equal to the probability of A and B, which is 1/6, right? Again, that's not a real great example because you could have looked at your diagram and came up with that, right? Okay, usually we would have solved it the other way. Okay, what they're getting at is that depending on what you know, you might have to solve for something else. Okay, so flip over real quick. I'll show you the examples that they're talking about. 727, 16 through 24. See how they gave you different information in certain ones? Everybody see that? You're going to have to plug in and solve for the unknown. Sometimes it'll be different. Does that make sense? And then they want to know, are they mutually exclusive? If they are mutually exclusive, this would just be 0. Because there would be nothing to subtract. So A and B would be 0. I think you'll end up figuring that out as you go. You'll come to one quickly. Okay. Now the last thing I want to look at here, before we start working a little bit, is on page 726 what they call the complement. Okay, so if I had something in geometry, we actually use the same markings for like translations, rotations, reflections. Okay, but we're going to use A prime. Okay, if you have an event A, okay, the complement of event A is A prime. Okay, and what this means, your complement is just going to be 1 minus event A. And that might be kind of confusing just talking about it right now. It'll make sense here in a second. Basically, what we're doing, you guys remember when we were doing our combinations and permutations, and instead of adding, we subtracted because it was easier? Same thing here. Okay, they want to know the probability of something, but instead of you counting to like 50, you could count to 3 and then subtract it from 1, is what we're getting at. So take a look at that. I think it's a dice problem here. Yeah. Okay. Your example 4, probabilities of complements. And it gives you, does everybody see, they give you all the different combinations for die when you rolled 2 dice there on example 4. When 2 6-sided die are tossed, there are 36 possible outcomes as shown. Okay, so there's a total of 36 because 6 times 6 is 36, right? For your combinations. Okay, find the probability of the given event. Okay, so the first one they want is they want the sum is not 8. Okay, so basically what they're getting at, and this is going to seem really easy once we get to the end of this, is it going to be easier to count how many there are where the sum is not 8, or is it going to be easier to count just the few where the sum is 8? There's going to be way less of these, right? Okay, so let's go ahead and count. Where's the first one we can find that's 8? 6 and 2. And then notice if you go diagonal up to the right, everything equals 8, right? So I have 6 and 2, 5 and 3, 4 and 4, 5 and 3, 6 and 2. So how many was there?
5.
There was 5 total, right? Out of 36, I know, correct? Now that's how many was 8. So 1 minus that is going to give me how many is not 8, correct? Okay, so that would just be using the complement. Okay, so we're using the complement or the opposite to figure out what we want. 1 is just 36 over 36, right? Minus 5 over 36 is 31 over 36. Okay, so it sounds harder when we start that out than what that really is. Okay, just basically you're saving yourself time by not counting how many are not 8. Now, most of you might have done that already without even talking about exactly what it is. Okay, let's do this last one. B wants to know what the probability is that the sum is greater than or equal to 4. Now, is there going to be more numbers that are greater than or equal to 4, or more numbers that are less than 4? There's going to be more that are greater, right? Okay, so we want to probably count the ones that are less, and that would make it easier for us. Well, 1 and 1 is less. 2 and 1 and 2 and 1, those are less, so we're at 3. And then that third diagonal row, those are all 4, right? So how many are less than 4? Out of 36, right? So to find the answer to this, 1 minus that, which is 33 out of 36. Oh, yeah. Okay, so basically what they're getting at is take the easy way out. Don't sit there and count to 33. Okay, take the easy way out and count the ones that don't work, and then just subtract. Okay, that's all the complement really is you're subtracting the ones that don't work. Okay, let's go ahead and do example 5 real quick before we start on our homework. It says 4 houses in a neighborhood have the same model of garage door opener. Each opener has 4,096 possible transmitter codes. What is the probability that at least 2 of the 4 houses have the same code? Okay. So we want that at least 2 are the same. Oops. At least 2 the same. Okay. Now we're basically back to our permutations. Okay, you guys remember when we did factorials, right? Okay. On top, okay, or I guess they continue to write, this would be the same as 1 minus that none are the same, right? Okay, so on top, I know I'm going to have 1 minus. Okay, this one's kind of confusing, their wording. Okay, the first choice I have, 4,096, right? The second choice, because I don't want them to be the same, so can there be this many on the second one? No, how many is the second one going to have? 4,095. And there's how many houses? 4. So now I need to do that 4 times. So 4,094, 4,093. Okay, so that takes care of all my 4 houses. And since I got rid of one each time, they're not going to be the same, right? Okay. Divided by, now I got to try to figure out what is the total possibilities or combinations that I could have here. What's that, Brody? Because for each one of those houses, there's 4,096 possibilities, right? Okay. So this is going to give me a kind of a crazy number. What does this end up giving me? It should be it's a ratio, so it should be between 0 and 1. Or excuse me, that's a probability also. Yeah, can you please? Well, 1 minus that is going to be 0.00146. Yep. Okay. What would this be as a percent? So what's the probability that at least 2 garage door openers have the same code? 0.146%. Basically no possibility, right? Not even a 1% chance. Not even 0.5% chance.
Take those odds.
Take those off. Not even a quarter. Okay? Before I let you guys get started on this, you guys understand 16 through 24? You're plugging that in. You're going to assume every single time, you're going to assume it's not mutually exclusive. Okay? If it is mutually exclusive, then your probability of A and B is going to end up just equaling 0. Okay, so just assume it's always assume it's not mutually exclusive, because if you subtracted 0, that's not going to make a difference anyways. Okay, so always just assume it's not mutually exclusive. I don't think that this one is quite as challenging as the last assignment, but there might be a few word problems here that are a little bit tough. We are going to add on to this tomorrow, so if you have questions and don't get it quite all the way done, that's not a big deal.